حسین بیا ببین من میگم هر چی تو ذهنم خیلی چیزاش من تو ذهنم نیست اونا رو تو تکمیل باهاش نیست باز کن من میگم آره من وای میستم نه
Right, folks, welcome in, welcome in. We're just getting the live stream going. Here it goes. So thank you once again so much for joining us this morning. We're so pleased that you could be here on this rainy Thursday for this walkthrough with Hossein Vatandoost and Alireza Moezi, who are both joining us in the sub-basements of the EV building this morning. We're going to be visiting a couple of labs and walking around a little bit, quite a few things to see. So very quickly, I'll pass it over to Hossein and Alireza. I'm not sure who we're starting with, but we're starting in the Smart Materials lab. So I'll pass it over to the folks in there now. Hi, good morning, everybody. Morning.
Okay. My name is Hossein. Yeah. Okay. Alireza, go ahead.
Okay. Welcome to our lab. My name is Alireza Moezi, second year PhD student at Mechanical Engineering. Our lab is located at EV building. The director of this lab is Professor Ramin Sedaghati, and we are working under his supervision. As you know, the name of this lab is Smart Materials and Adaptive Structures. The general definition of the smart materials is a materials that can remember some forms and act upon applying the stimuli, such as magnetic field, electric field, humidity, and etc. For example, if you consider electric field, we can have a piezoelectric that can react upon applying the electric field. This kind of piezoelectric can be used in the actuation purposes and for the sensors. You can see, for example, we have here some accelerometer that all of these accelerometer take the advantage of the piezoelectric, or we can see a kind of piezoelectric valves that can open and close the valve using the advantage of the smart materials such as a piezoelectric.
Very good. Good morning, everyone. My name is Hossein Vatandoost. I'm a postdoctoral MIAE Department, supervision of Ramin Sedaghati and Prof. Subhash Rakheja. We are working in the two labs. This lab is a smart material laboratory, the EV building, and mainly working on application in a relatively large scale compared to Alireza, which is mainly working on small scale application of smart materials. In the second half of this today lab watch, I will explain some of the application in the downstairs, the 3 floors, and Alireza is going to give you some basic phenomena of smart material, particularly those that are show the response with respect to external magnetic field. So Alireza, go ahead and give us some fundamental.
Here, our main focus, as Hossein said, is magneto-rheological material. It means that this kind of material can react or respond upon applying the magnetic field. We have 2 well-known categories of this kind of material. Is magneto-rheological fluid. It means it's named MRF, and the magneto-rheological elastomer. It's named MRE. And here the main research is on the magneto-rheological fluid and magneto-rheological elastomer. If you would like, I can show you.
Yeah.
Here we have a kind of MRF. This MRF consists of iron particles and a kind of oil. Here it's a silicone oil. These iron particles inside the silicone oil, and upon applying the iron particles create a kind of chain-like structure in the direction of the magnetic fields. This is a kind of application of this MRF. You can see that you can push this plunger very easily. But when you applying the magnetic field, these materials stiffer, and this viscosity will increase, and you can not push it very easily. You needed too much force, and this is one of the application in MR damper for suppress the vibrations. And here, this is the MR elastomer, the second type. As you see here, we have a silicone and the iron particles. In the fabrication process, we put the iron particles inside the silicone to MRE here with different volume. And here it is 25% volume fraction. The difference between this and this is that when you put it more iron particles inside the silicone, you have a more MR effects. It means that you have a more deformation or more response because of the iron particles. And here we have a carbon. This kind of iron used inside this material, and you can see it here.
Can you show the flexibility of the material?
Oh, okay. You know, it's very flexible. And if I apply the magnetic field, you can see it. This kind of material can be used in a vibration isolator and so on. If you want.
So just one comment toward this fluid. Basically, MR is a stand for magneto-rheological. Rheology, science of deformation, as you know, and this type of material has two main parts. One are a tiny iron particle. Usually, the diameters are ranging between 1 to 10 micrometer, and the second part is the carrier for a non-magnetic medium. Doesn't respond to the magnetic field, unlike the iron powders. When we mix the two, carrier fluor and iron, we will have MR material. This carrier can be different material. If the carrier is fluid, we would have MR fluid. If the carrier becomes solid-like material such as gel or elastomer, we will have solid-like MR material, so-called MR elastomers. There are pros and cons. MR fluids, there are some drawbacks, such as sedimentation of iron powder after several hours. As you can see, this iron powder sediments after several hours. So we need to disperse these MR fluids. So these are basically the principles behind this MR fluid. Is just as Alireza showed you, when there is no any external magnetic field, these are like a fluid-like material, such as you can imagine as a milk. But when you apply external magnetic field between each individual iron particle, there is a induced magnetic field. So these people interaction collectively make the whole structure solid-like. You can imagine the milk can change into the cheese, so it becomes very stiff. So the principle just they have to remove this. Your force should exceed the amount of yield stress in order to allow the material to shear. So it has lots of application in variable damping, such as dampers for automotive sections, in military application, and conventional dampers. They are very large and heavy, but with this type of damper made of MR fluid, you can reduce the weight and thereby increasing the mobility of the structure and make them lighter. So, these are these solid-like elastomer, and they have very they can experience large deformation. The carrier is silicone. Silicone is not black. the reason that the color is black, as Alireza mentioned, is because
of
the
iron.
iron. So Alireza, go ahead and
Okay.
complete other.
Here we have a kind of binder that we are using for a kind of the coils. As you know, the stimuli can be a permanent magnet or electromagnet, but for the permanent magnet, you don't have a control on the amount of the magnetic field. But by using this kind of electromagnet, you can control the current that passes through the coil, and you have a control on the magnetic field, and you can have a better response from your MRE or MRF. So also here, we are using this kind of device. It's a we are using for field by using this electromagnet to see the response of the material. Also, this kind of rheometer has a advantage or take the advantage of the changing temperature. You can change the temperature and see the difference in the response of the material because the MRE is a very heat sensitive. Also, as you see here, this is the result that we extracted from a kind of sample. We see here a storage modulus and the loss modulus. Here, the storage modulus is the ability of the material to elastically, and the loss modulus is the to dissipate heat. Like we can predict the behavior of the material. Also, based on the experimental test that we are doing in this laboratory by using this rheometer, we can make a comprehensive model, mathematical model for this MR elastomer, and we can use it in our simulations to predict the behavior of the material.
You only applied with the magnetic field to the material. But now you're seeing with this machine, you're able to apply both a magnetic field and also a change in temperature. So what does this, what's the difference when you apply both to the same material?
You know, as I said, that experimental test just for showing the behavior of the MR elastomer. Device that can help us to measure the ability or the response of the material when you are applying the magnetic field and the temperature. As I said, this kind of materials is heat sensitive, and in the various temperature, you can see a different responses. And it's very important because, for example, if you are making a coil, by increasing the current, the temperature of the coil will increase. And because this coil will be installed on this MRE, you can see the response of the MRE now is different because of that coil. And here we can measure this response with this device before making the structure, something like this.
Very good. Just one small comment. If we consider this solid like MR elastomers, okay? So, for example, you can consider these very soft cylindrical MRE samples. This MRE can operate between two plates and can experience shear deformation. Okay, can experience shear deformation. There is, or you could say, torsional deformation, which is related together. Or you could compress. You could compress mechanical loading and also in parallel magnetic field. So we want to know how this material reacts to external force and external magnetic field. Because this is a part of we call it characterization of the material. So we need to know how they react to mechanical and magnetic field force before designing smart devices based on a smart material, because we cannot randomly design a smart structure. Our budget is limited, our time is limited. So we need to model. For modeling, we need to characterize it. So this device is mainly dedicated to shear mode characterization, shear mode. So a specific sample geometry should be applied under this rheometer, mainly cylindrical sample, diameter of 20 millimeters and thickness of 1 to 2 millimeters. And this spindle from the top goes down and attach this MRI sample and create rotational deformation simultaneously perpendicular to the surface of the sample. There is a magnetic field coming from this electromagnet inside. So we vary the angle of deformation, large deformation, small deformation. We vary the frequency. Their behavior depends on the frequency of oscillation. At the same time, we vary the magnetic field. The more magnetic field, the more they become stiffness. And we see their properties, as Alireza mentioned, the storage properties, how you could, how they store energy, and dissipate properties, how they damp energy. And we need them for the design of structures. Here is smallest scale, soft robotic, or largest, for example, vibration devices, vibration isolation devices. And Alice, go ahead and go for the next equipment.
Here we have a shaker. With this shaker, we can create a different excitation to the structures. It can be sinusoidal or random excitation. And upon applying the excitation, we can see the response of the structure that we made. For example, this is a kind of vibration absorber, a sandwich beam that's fabricated by graduated master students. You can see here the coils. It has several coils, and here it is a MRE between these two steel plates. And upon applying the magnetic field and the excitation using this shaker, this kind of sandwich beam starts to vibrate. But this MRE can help us to suppress the vibrations, and it's very important for some applications. So by using this device, we can create several excitations modes with different frequency, different amplitude, and see the response of the structure. Here it is a kind of accelerometer that we installed on the base. Also, we will install a second accelerometer on the structure to see the different response than this accelerometer. The term here is a transmissibility. It means that the response of this structure than this base, and if it is lower than 1, it means that this MRE worked and helped us to suppress the vibration. If you have any comment, Hossein.
So basically, one question I noticed from our initial Zoom meeting, it was, what is the difference between a smart material and smart structures? So as you can see, this is a smart structure because it includes some MR material, which is clamped into aluminum parts. So this is called vibration absorbers. So we have a main system which is oscillate. So we want to reduce the vibration of the main mass, which is very important. So we added additional mass and spring on the top. We don't care about the movement of the small mass. So we need to just reduce the vibration of the main mass. We add a vibration absorber like this system. So we design in a way that the natural frequency of these absorbers is equal to the excitation of the main mass. If we do so, the excitation of the main mass surprisingly becomes 0, and the absorber will oscillate. We don't care about the oscillation of the absorber mass. We only care to reduce the vibration of the main mass. So if we use passive spring, it only works for just one frequency, 2 Hz. If the excitation of the frequency vary, the main system becomes vibrating. You can consider it as a washing machine. So, but if you put MR elastomers material here, by varying the current into this coil, vary the magnetic field, could vary the stiffness of the material clamped between these two aluminum sheets. Thereby, we could follow the we could vary the natural frequency of the absorber mass, and we could reduce the vibration of the main system for a relatively large range of frequency. So these are just characterizations desktop that could be open and controlled. For a control, we have to just get a feedback from the external, from the accelerometer, and apply a specific current in order to match the frequency of the absorber to the excitation frequency in order to real-time reducing vibration of the main mass. So, Alireza, you are going to focus on magnetic property of the device that you design.
I'll hold the microphone for now so we can go back and forth.
Here it is a vibrating sample magnetometer that I fabricated in Concordia University as part of my thesis. As I said, with that device we can measure the mechanical property of the elastomer that we fabricated. By using this device, we can measure the magnetic property of that elastomer, such as the magnetization, permeability, saturation level, and so on. If you would like, I can show you the here, this is the change in magnetic field, and we can measure the difference in magnetic flux density. It takes about 10 to 15 minutes to measure to finish the measuring process. If I want to explain this device based on the Faraday's law of inductions, here this is the magnetic object that's installed on this probe. This probe oscillates or vibrates vertically inside this magnetic field. This is a coil that applied a perpendicular magnetic field to the object. With this movement, a kind of current or EMF will be induced in the pickup coils that I designed for this device. And this kind of amplifier can measure the amount of the current or the voltage. And based on the code that I programmed, we can measure the data very easily. It is very important because we can see the behavior of the material under different magnetic fields. And for most of the simulations, you need to define some magnetic properties as a parameter in your mathematical model. With this curve, you can extract these parameters. And here I use this function generator to create signals. That signals will go through this amplifier and amplify, and by using the amplified signals, this kind of vibrator here can move vertically with different amplitude and frequency. Also, one of the advantages of this device that I fabricated here, you can rotate the objects and see different responses. And if you want, I can show you the object that I put it inside this device. As I said, it takes several minutes. So I can. Change the sample here very easily. And you can see here, this is a piece of MRE that I put it here on this sample holder. And when you put it this MRE inside the magnetic field, as I explained, with this device, you can measure the magnetic property of the MRE. And here, I fabricated that can print different MRE. My topic in this group is a magneto-active soft robot for biomedical applications. As you know, today's many robots developed for several applications. Now, developing a small-scale magneto-active robot for medical application is a hot topic. And here, my main focus is on developing this kind of robot and the simulation, the behavior, and finally control this robot inside liquid or on the ground or through the human body. I can run this. Because I can't make a comment on any other devices.
So, okay, no problem. So for the this electromagnetic device can also be used for fabrication of MRE. Basically, MRE is magneto-rheological elastomers, MR elastomers, and for fabrication, all you have to do is just mixing iron powder with silicon. As soon as you mix them for time of 5 minutes, and then degassing the mixture. There's a device there I can show you for example, when you mix the iron and silicon inside a mold and put the mold inside this vacuum chamber, the air bubble will be removed, and then if we pour the mixture in a specific mold, after 24 hours, you will have isotropic MRE, which means that these iron powder randomly distributed among the matrix, which is the material properties is identical in any direction. However, if you put the mold inside that magnet, we could permanently align chains of iron particle inside the matrix. So at the end, once the material is fabricated, we call it aligned MRE or a structured MRE or anisotropic MRE. This type of material has different magnetic response perpendicular to the chain and in the direction of the change. In the direction of the change, if you provide electromagnetic field, it will give you higher MR effect, which is defined as variation in the material, either a stiffness or damping properties, which is very important. So these are two types of MRE fabrication, isotropic and anisotropic, which for the latter we need a huge amount of magnetic field. Another important part would be how much iron we could put inside this silicon. So there is a term volume fraction or weight fraction. For example, 10% weight fraction of total mixture is iron, or 20% or 30%. How much you have to put iron with respect to this matrix silicon? So researchers have done lots of tests to understand which volume fraction is the best. So usually 30% volume fraction of iron will give you the maximum MR effect. And for the anisotropic MRE, if you fix, for example, if you fix the volume fraction, for example, 20%, the amount of field for fabrication of anisotropic MR is also important aspect for material response. The more you provide external magnetic field during the fabrication, the particle gaps become decreased and the number of chains decrease, and it has more, it give you more magnetic properties in parallel to the change because of these particle gaps. I wanted to highlight the fact that there are many factors that affect these materials: shape of iron powder, or their diameter, their shape, size, and also additives will make difference. So Alireza, it's okay. So, and this is these for the fabrication purposes. We should like to go for, okay, we can go there, and
We need to take a pause. We can take a
okay,
pause.
no problem.
That I fabricated in Concordia University as a part of my thesis. With this 3D printer, you can print MRE-based material. For my thesis, because my main focus is on the small scale soft robot, I use this kind of 3D printer to fabricate magneto-active soft robot. Here, this is the process, but I did this or develop this soft robot by using this 3D printer. Here, this is a different shape. You can see it's a petal. It's a structure with several holes. And if I apply the magnetic field, you can see the response of this petal, for example. And for this structure, the structure will be different after applying the magnetic field. It can move or wax. Open applying the magnetic field. You can see here. Also, it can rotate. Something like this. And here, the rectangular type soft robots, different response. I don't know that I can do it or not, but if I put it an object here, maybe I can deliver it. It's a bit difficult, but it's possible. It can deliver, but it's a bit with this
That one
permanent
will
magnet.
be simpler, right? With the other one for delivering the.
Yes. Also, this kind of robot can be used for delivery, you know, because this is just permanent magnet and the operator is me, you know, it will be difficult. But if you put very big interface. Yeah. If you have any question, we can respond because now I think it's finished.
Yeah.
The demonstration.
Yeah, I do have a question for you. So one of the students wanted to know what gets you most excited about which machine, let's say in your lab, gets you the most excited, or which project you're the most excited when you wake up in the morning to come into the lab to work on.
Or the machines that I fabricated by myself. Actually, this 3D printer, because we can make a different type of small scale robots, and after that, and I think this is the best one in my research.
Maybe we could go to your lab now.
Okay.
Perfect.
And Anna, if you want to spotlight the card, we're going to do a transition to S3. There we go. Thank you so much.
You're welcome. Thank you very much for your visit.
Thank
so,
you so
so
much.
great to see you. Okay. One moment. Okay, we are moving to S3 now with Hossein. I can't hear, but Makai, I think, can hear. Makai, can you, how was the sound when I was moving the mic back and forth? I couldn't hear.
It was
Okay,
good,
so
yeah.
I'll keep doing that even.
I guess it's just kind of like
Maybe for Hossein, I can
less room.
clip the mic to him if it's just him. So I'll leave it this way. Okay. Thanks everyone at home for, yeah,
Some good moving.
Great work, guys.
there's some
And
advantages.
you take control.
I'm also stealing their pen. We're going to use the elevator, so we might lose connection. We'll check when we get through. We'll see. Not sure if it will restart. In the S2 elevator going down. Did we survive that? Three connections going? Okay, do we have three connections going? Yeah, you've got iPad, mic, camera. Great. Really walking labs. Okay, we're in the lab space now. Hossein, if it's just going to be you,
Okay.
I'll clip the mic on you.
No problem.
Then I don't have to move it so much. Okay. So don't get yourself ready. You need to prepare. Yep. Yep. Okay.
Thank you very much. Hello again, everyone. Welcome to the Concave Research Laboratory, Concordia Advanced Field Engineering Laboratory. The main focus of this laboratory is to assess the human response to the vibration. It can be varied to seat position. Here there is a seat suspension system that can apply from the bottom by these two actuators different types of vibration to the seat, and the people will be sit on this device, and these are accelerometer, as you could see here, attached to the base and attached to the top. We can measure the input accelerometer and also output accelerometer. We divide it by 2 in a transmissibility function, and we will see in a different type of, for example, we could simulate different bumpy roads, apply different type of vibration, white noise, different stochastic vibration, and measure the transmissibility and output acceleration, and to see which type of spring and damper we could use. For example, usually there are some dampers and springs. So the seat suspension is usually used in order to reduce the vibration transmitted from the cab floor of the car, which is related to the wheels, in order to isolate them and reduce the vibration transmitted to the seated occupant. Because annually, according to the research data, these drivers for countries has shown that there are lots of chronological disease associated with the back pains, and so we need to reduce this amount of vibration, which is very tricky. Design of this seat suspension is not easy, because in the static case, this spring and damper should tolerate the weight of the occupant, seated occupant, and we need high static stiffness. In the dynamic mode, we need to have a softer stiffness to isolate this natural frequency of human body between around 4 to 5 hertz. So we need a nonlinear spring, nonlinear vibration system. So it is not an easy task. Usually this seat suspension divided in can be categorized in 3 sections. One is a passive system. Passive system, it means just passive spring and passive damper. Their properties such as stiffness and damping are constant, irrespective of loading condition. The other types are active system. I can show you there. If you come here, I can show you the active seat suspension system. So these are some actuator, different type of actuator can be used for active suspension system. So there is a force from the bumpy road from the lower part,
and this active system create force to contract the force coming from the rods. So these active systems are trying to contract the force and reduce finally the vibration, which is being transmitted to the seated occupant here. So these are really very complex. At least $6,000 to the car. Many cars has these active seat suspensions. So these are quite heavy and very complex. But not all of the cars use this active seat suspension because there is a possibility of miss current and miss force, and to double the force, rather than contracting the force. So the researcher usually try to use this third type of seat suspension system, so-called semi-active suspension system. In a semi-active suspension system, we use MR damper. This is the MR structures. Inside is MR. These are MR fluid, and so we could vary the properties of this fluid inside this structure by applying current to this very small electromagnet. We could vary the viscosity of the fluid, and we could have a wide range of dynamic force in order to reduce the vibration. It will not reduce as compared to those active, but these are quite simpler, quite cheaper, and quite safer compared to those active systems, and can give better results compared to the passive suspension systems. And yes, go ahead.
Hossein, what would you say is the biggest challenge to work with materials that are so sensible to vibrations because of your work and because of these two projects that you're working on simultaneously?
Right. So you mean what type of? I didn't get your question. Sorry.
I was asking, what is the biggest challenge to work with materials that are so sensible to vibration?
Okay. Basically, very good questions. Because both MR fluids and MR elastomers are highly depend on the amount of deformation in terms of amplitude, and also rate of amplitude. So this material and structure are load dependent and rate dependent, both of them. You're amplitude dependent and rate dependent. And so we have to come up with a model that can predict the output force as a function of amplitude, as you mentioned, and rate of deformation. Apart from that, these are highly, this smart structure, one limitation is the temperature. They're quite temperature dependent. However, these MR damper fabricated by Lord Corporation have lots of additives that can work with a relatively wide range of temperatures. And some researchers use some fins in order to increase the heat transfer, and that allow the damper to work in a very harsh conditions. So I want to answer your question. This is for MR dampers. Fluid inside it has a MR fluid, and my research in my PhD was on the characterization of MR elastomer material. I can show you several samples here. As I mentioned, this cylindrical MRE samples can be fabricated by different amount of iron powder. So these samples are quite soft, containing only 15% of volume fraction. These are a little bit stiffer compared to this 30% volume fraction, and these are quite stiff. These cylindrical MRE samples. So this, in order to see how they react to the external loading and magnetic field, I designed a electromagnet here. This electromagnet has a U core, English letter, and I core here, and containing three windings, and we could put the sample here, and we could assess the characterization of the material, static and dynamics, how they respond to mechanical and magnetic field. As I said, there are mainly two modes of operation, shear and compression. Here, my focus was to assess the properties in the compression mode. So unlike the shear mode, it is very difficult to provide magnetic field simultaneously parallel to the mechanical loading. The rheometer can easily create a shear deformation while providing magnetic field perpendicular to the shear deformation. It's a very easy task. However, providing field and mechanical load simultaneously is quite difficult. And we need to come up with a design that allows both mechanical and magnetic field simultaneously in one direction. So I can start this is a ANTS machine material testing system. This is a load cell, and this is the actuator from the bottom. It can apply different type of deformation and oscillation, and the output force will be measured by the load cell, and will be analyzed. We do the analysis with the software such as LabVIEW, and record the data for different wide range of loading factors such as amplitude, rate of amplitude, and amount of magnetic field. So I would like to stay over there because I want to turn on this MTS machine and show you how we could do the characterization of this smart material. So, so I want to just turn on the machine. So if it is better for the sake of safety, it's always stay here, and it is a little bit noisy. I'm not sure whether you will hear my voice clearly or not. So this is the controller, and it can provide different type of loading to the samples. And for example, amplitude, frequency, and for the magnetic field, I connected the wire of this coil to these power suppliers to provide required current to energize coils to provide magnetic field. And so today I'm gonna show you how we could do the characterization of the MRE material under compression loading. And so I will try to apply some dynamic loading. So I'm preparing this controller for applying the sinusoidal deformation. So here, as you could see, different type of waveform can be applied. I do use the sine form. You could vary the frequency here. So I will keep to the 1 Hertz just as an example. And so for the start, I will put the sample. I displace the sample toward up, because from the top sample will be connected to the Y part of the electromagnet. And as you could see, so I will try to connect these two samples to the top, which is attached to the load cell from the top. And normally these material experience a static deformation due to the payload. So there's a static pre-strain deformation. I will apply a 10% static pre-strain before applying harmonic oscillation. So I think, okay. So I'm going to apply the harmonic oscillation. So as you could see, there is a movement. I can go up and little bit increase the frequency. Around 1 hertz, the frequency of oscillation. So now I can put it in around 2 hertz. So there's a sinusoidal dynamic loading is being applied to the samples. And if you could take a look at here, there is a software that you could analyze this. So there is a force displacement. This is a so-called hysteresis phenomenon, which is come from the viscosity of the elastomers. So the energy will be dissipated during each cycle. So unlike this passive spring here, this is the passive spring. If you displace, and it will give you the same amount of energy. However, this material, because of its viscosity, some part of this energy will be dissipated, and the area inside this hysteresis loop are associated with the damping and dissipative properties. So if I increase, this is a force displacement when there is no external magnetic field. And if I apply the electrical current, the material should be stiff. And so I will increase the voltage to, so you see the area and the properties of this, the force also decrease, because under compression, tension will give positive force and compression will give negative. So the force changes from around 30 to around -50. If I increase further, so even more force will be generated inside the MRE. So this shows this property dependence. Stiffness and damping can vary by applying external magnetic field. So as soon as I remove the external field, the force will be vary. So we could measure this both stiffness and damping properties to come up with a model, and then use this model for designing smart structures. So I will, so this characterization, as you mentioned, can be implemented for different range of frequency and electrical current and loading, which is required to come up with a model for further simulation and do the analysis. So I will turn off the device and I will try to explain some other equipment. Yes.
When we first enter your space,
Right.
first we realize that there are yellow beams that are all
Right.
around,
Right.
and there's also this beam in the floor.
Right.
So I'm wondering, can you speak of these architectural aspects of your lab and how they influence your work ultimately in your practice?
Sure. These yellow structures are specifically designed for allowing these very heavy-duty cables, which in order to energize these very electrodynamic shakers. This lab is specifically designed for vehicle engineering application. There are lots of mechanical shaker to apply different range of mechanical oscillation. This is MTS machine. There are also other MTS machine. And here I can show you, for example, if you want to simulate for example, 3 floors building. So you could put a small scale building from over this shaker table and apply the mechanical oscillation from the bottom side, and we could apply oscillation to the small scale building and put accelerometer in the different floor and measure output accelerometer for earthquake engineering application. So which type of laminated rubber bearing can we design in order to reduce the accelerometer and displacement of each floor with respect to different type of excitation related to the, for example, earthquake. And these are these actuators, and one of the main work has been done from many years ago. It's just seat suspension system, because it's a very difficult task, because different driver, female, male, weight there are many parameters that can affect this design of this seat suspension. So we need to do the large range of tests in terms of materiality, such as cushion. Also, another PhD student is working on the seat cushion tests, different cushion tests, and see the result of this cushion in the dynamic response. And another PhD student had been working on these anti-vibration gloves. So, because many operator, for example, when they work with the drills, their hand experience a large amount of vibration, and there is lots of disease associated with when people exposed to a large amount of vibration daily, hand-arm vibration called. And industry has come up with the solution. They attach a layer of rubbers, air spring, different type of material in order to reduce the vibration transmitted to the hand. However, if you put layers of layer, but then it is not easy for you to work on, and dexterity would be decreased if you increase the thickness of this material. So we need to do both mechanical characterization and dexterity tests at the same time to come up with a trade-off, which the optimum layer of thickness of the rubber, for example, that gives off minimum amount of vibration isolation and at the same time enough amount of dexterity. So this shaker is being used for applying mechanical oscillation, and this accelerometer is designed to attach to these gloves to measure the external force. And by this computer, we will assess the vibration transmitted to the hand by different parts of the palms of the hand and arm. And then we will analyze the data and do the parameter analysis to come up with the optimum structure and compare different type of gloves. Which one is better, rubber, air spring. So this can also be, in my research as a postdoctoral fellow, one of project would be using these passive rubbers. We could apply more elastomers layers, so we could have some more variation and put adaptability to these gloves. So in order to come up with better vibration isolation, at the same time higher dexterity. And Yes, go ahead.
So my question is, obviously there are such amazing projects in this space, and Rebecca Duclos and I are so lucky to be here and explore your space with you, also explain everything. But I'm wondering, for the students who are looking at this lab walk, how would it be possible for them to follow the advancements in their research, or how would it be possible to have access to this space, even if I don't know if this is something that you usually do, but if ever they want to follow your studies, how would it be possible for them to do so?
Okay, no. Thank you for the question. I have published several research articles, and in my Google Scholar, they can access to my Google Scholar as well as the LinkedIn. And currently, we are collaborating with Art and Science Department with Professor Alice Jarry. We are working with some materiality, designing some smart structures based using some PZT material, MRE material to come up with a novel structure in terms of actuating and sensing both simultaneously. And so I would like to ask a student, feel free to send me an email to have discussion in order to visit the lab, or to do some discussion about in terms of materiality and application. And I will try to reply them and be engaged and talk about their questions and answer their questions. I would be very happy if there's any questions.
So I'm wondering, what are you excited about for the next 5 years, let's say, in the field of smart materials, and into your own research also? What are you expecting for the next 5 years, or what would you maybe desire to happen?
Okay, that's a great question. I would like to answer your question by showing you that damper. Sorry. So, my focus is on magneto-sensitive material, MR elastomers. MR material has two branches, mainly MR fluid and MR elastomers. MR fluid, there is a commercial application, MR damper. However, there is almost no application of MR elastomer because of the challenge associated with providing magnetic field. We normally require very strong electromagnet because the thickness of the rubber is quite large compared to the gap thickness of this MR device. So for example, for 1 millimeter, we could up to 900%, we could increase the viscosity of this MR fluid inside this damper within a short, just 20 milliseconds. Compared to those other smart material, one ruler should be response time. So these are very important aspects. So both of them are around 10 to 20 millisecond response. And it is very difficult to provide magnetic field. I'm trying to address this challenge to come up some a specific design of electromagnet, some other solution to reduce the weight of electromagnet, which is almost 5 kilogram electromagnets, to provide around 1 Tesla magnet to the 10 millimeter thickness samples. It's very difficult task. That's why almost no commercial application of MR elastomers as compared to those MR fluid dampers. So this is my primary challenge. I've been working on it in my postdoc. I'm trying to address this challenge during this research program.
Is there one last thing that you want to show us in your space, or how would you like to conclude this lab walk, just to finalize this great discussion that we have?
Okay, that's a very great question. The final remark would be on this seat suspension system. So there are many research that have employed and designed MR dampers to the seat suspension system, but lower amount of work have been using MR elastomers to do a seat suspension and cushion. I'm trying to integrate the cushion and seat together to come up with a lightweight seat suspension design. utilizing the MR elastomer material. And thank you for your visiting to our lab. I would be very happy to have more lab walks again. I would be happy to answer your question and show you our results in the next stage. Thank you very much.
Okay, folks, thank you so much, Hossein. Thank you, Alireza, for being with
Anna.
us. It's been really such an honor and such a pleasure for you sharing not only your projects, but so much of your time and preparation in order to show us around. We really, really appreciate it. So thanks everybody for joining us and for doing such a great job navigating all those spaces and variety that we saw today. Okay, folks, we're going to close the Zoom. Have a wonderful rest of the day.
Thank you for your time. Thank you so much.
Bye-bye. Cheers.